After a couple of hours of troubleshooting this Excel sheet from this practice problem from last time, I'm sorry to report that I was unable to find the source of the error. However, I wanted to talk more about it in the first video because I still think there are things to learn from this example, even though we can't see what the exact numbers are going to be. What I've decided to do for this problem is I'm going to talk through it, and then even though I didn't find my mistake, I'm going to open it up as an extra credit assignment. So I decided that it's going to be worth 30 homework points if you can properly figure out what my mistake was and get this Excel sheet working such that you can get the accurate PXY curve on your own after you see what I've done. So just as a reminder, what we're trying to do is we're trying to use Phi-Phi modeling to use the Peng-Robinson equation of state to predict the PXY diagram for propane and butane at a specified temperature. Recall that we've set what the temperature is, and we have a choice to set either X or Y. I've elected to set X such that we have three equations that we can solve for. The two equilibrium criteria, which are a function of the mixture fugacity coefficients, which we'll have to calculate, and the constraint that the pressures of the two phases must be equal. So recall that the mixture fugacity coefficients can be calculated with the following equation, where this is a minus down there, so be sure to fix that. That was the one mistake that I found, and I'm not entirely sure. I've looked over my equations for phi multiple times. I was not able to find a mistake there, but it's possible that I have a mistake there. These phi's are a function of A and B, which are the Peng-Robinson coefficients, which can be found by the following formulas, which are a function of the pure component Peng-Robinson coefficients, which are themselves functions of the critical temperature, critical pressure, and omega, the acentric factor. So this is again how you find the phi1L, phi1V, phi2L, and phi2V. The last equation, which is the equality of pressures, the condition of mechanical equilibrium, can be found by using the Peng-Robinson equation at the two phases, for the two phases, to find what the molar volume for the liquid and the molar volume for the vapor is. I actually think this is another one of my problems. I'll talk about this later, but remember how if you're solving this equation, you have to have an accurate first guess for the molar volume of the liquid. Otherwise, solver will only return one of the roots. It won't necessarily return the root that corresponds to the actual one. So that's a possibility as well. All right, so going through how I went about solving this problem, you first set a range of x's. So I've set 50 data points for the x. The y, remember, is unknown. So this y contains values that I've used solver for. So in my troubleshooting process, I've tried to use solver to solve for y. This pressure is the pressure that I'm going to plot. This pressure I've set an equation for. So I've added two columns since the last time we've had class for the pressure of the vapor phase and the pressure for the liquid phase. This is calculated by the Peng-Robinson equation of state. And these two things should be equal. So you can just take either one of the pressures. I chose pressure of the vapor for whatever reason. It could be either one again. And divided it by 1,000 because this pressure is in pascals and I want my pressure in bar. 100,000. Right, and then I have A and B constants for the vapor and the liquid phase. And remember, I need two separate numbers for the vapor and liquid phase because the compositions will be different in the liquid and vapor phase. So therefore, my mixture A's and B's will be likely different. So notice that my A and my B for the pure component is going to be the same. So there is no difference in A of the vapor and A of the liquid if I have a pure component. And that makes sense because my composition is the same, therefore my A value should be the same. And it also happens to match the pure component value from component 2. So if I check all the way at the other end of the spectrum, I should have, oh, maybe this is, oh no, because it's a function of y. Right, my A of the liquid should match what my pure component is for component 1. This one should be, it should match as well, right? Because I know that when I have pure component 1, then I must have pure component 1 in the vapor phase as well. So I'm getting agreement here, 1.099, 1.099. All right, and same thing for the B. At the pure component, it matches the value for pure component 2, and it is the same for both phases. And same thing down here. All right, molar volume of the vapor and molar volume for the liquid are my two other unknowns in addition to Y. So I have three equations, three unknowns that I'm going to use to solve my system of equations. So these just contain initial guesses. So this is what I was talking about. I'm going to need a good initial guess for the molar volume of the vapor and the molar volume of the liquid. Z, the compressibility factor, is PV over RT. So PV divided by RT, and if I looking ahead to the PV equation, this is the equation from the Peng-Robinson equation of state. So RT over V minus B minus A over V times V plus B times V minus B. And that was another mistake that I think I caught, that this is supposed to be a plus, via the liquid plus B and via the vapor plus B. But I fixed that, and I'm still not getting it to work out. So again, there's still a problem here somewhere, still trying to work through it. Z for the liquid is the same thing, PV over RT. The only difference is you're using P from the liquid phase and V from the vapor phase to get your Z's. Now the Phi is the long equation. I typed out the first one on Monday, and I don't think there was many changes from that. Only difference is, again, this is supposed to be a minus. So again, pause the video, check through this. I'll do the same thing for Phi of the liquid. So I skipped ahead and I typed this all in myself. You can double check that I've done it correctly. Again, I wasn't able to detect any obvious mistakes that I've made. Maybe checking these, just double checking to make sure that you're referencing all the cells that you want to reference. And same thing for Phi 2 of the vapor phase. So go ahead and pause and double check, comparing it to what it's supposed to be. So maybe I'll put the equation there. All right, and pressure of the vapor and pressure of the liquid is again given by Peng-Robinson equation of state. So I had a lot of things I troubleshooted or I went through. The first thing is I had a number error sometimes, and this occurs because I have a negative pressure there, so therefore I have a negative in the LN term. I wanted to again call your attention to, if you're having a number error, what you can do, or one way that you can double check it, is you can click on the exclamation point and show calculation steps. And here it highlights for you that the next evaluation will result in an error, and it's in italics here. So I have minus ln of a negative number. So this tells me that whatever is in the ln up here is going to be negative. And in this case, it is because I have a negative pressure. All right, so if I click on this formula, Q16, so I'm multiplying by a negative number, which means that it's going to be negative. All right, so all I need to do here is double check, why am I getting a negative number? And that is because I've got a molar volume for the liquid that is out of line from expectation. So if I just copy that value down, it should go back positive, and it shouldn't give me a number error anymore. Again, that's not going to fix the problem. I'm just trying to work through and troubleshoot all the things that it could be. All right, so now ignore these three columns for now. After all this is set, I have enough to solve these three equations. So that's what I've done here, is I've set three columns for equation 1, equation 2, and equation 3. And the formula for equation 1 is I've just written what I have in the first equation. So I'm doing what I usually do, taking everything over to one side, setting it equal to 0, such that solver is easy to set up. So I've got x1, phi1 liquid. So x1 is A9, phi1 liquid is M9, minus y1 times phi1 vapor. Y1, phi1 vapor. And because x and y are both 0, this one will obviously be 0. This one's a little bit harder to solve for because of these zeros, like I said. So when I was using solver to troubleshoot it, I was always doing it with the second data point here. Equation 2 is the same equation. So it's y2 now instead, x2 now instead, which is 1 minus A9 times O9, which is phi2 liquid, minus Y2 times Phi2 vapor. And this one should be 0, so I need to goal seek that to 0 in order for the equation to work, or solver it to 0. Equation 3 is the third, and I want to set my pressures as equal. So what I did here is I looked up, or I calculated what the vapor pressure was for pure butane, because I knew that at pure butane, it's got to be the vapor pressure. So I used that to try to use goal seek to solve for the molar volume of the vapor and the molar volume for the liquid. And this is how I started off my calculation. So solver, for whatever reason, didn't work after this. So I'll show you what I was attempting to do. So you click Data, Solver, and I want to set my objective to be cell R9 to a value of 0, because all three of these have to be 0, by changing variable cells of my unknowns. So I've got Y, and I'm holding Control and clicking to select multiple. So Y and the molar volume of the vapor, molar volume of the liquid should be my changing cells. And then my constraint is that my other two equations must also be 0 as well. And click Solve. So when I do that, I do get an answer that sets them all equal to 0. However, my pressure is much lower than I'm expecting it to be. Remember, this pressure needs to be what the vapor pressure of pure N-butane is at 323.15 Kelvin, which is, again, on the order of about 4 bar. So that's how I know something is off here. If I can't get it to work for the pure component, it's very unlikely that I'm going to get it to work for any of the mixtures as well. But that's, in general, the algorithm. So I'm doing it line by line, even though I could do multiple lines at a time. And as you saw in my solver, that was the last thing I did, is I tried to do multiple lines at a time. But while you're trying to get it to work, I suggest doing it one line at a time. So if I instead click, the next line would be R10 by changing variable cells. And this is, again, a little bit slower than it should be. But you really have to go this slow when you're doing the troubleshooting portion, because if you don't go slow, then, and you're trying to do too many things at once, it could be too hard to keep track of. So click Solver again. Solver could not find a feasible solution. I'm not sure why that is, why Solver's having such a difficult time finding values that work. I mean, well, this looks like it kind of works, right? I mean, it's in line with what we were expecting. So we expect the pressure to go up, and we also expect Y to go up as well. I'm going to pause one more time and try one more thing that I just thought about. But other than that, this video is almost complete, and I'm going to stop it there in the interest of moving on to other more interesting problems. So the brainwave that I just had was that, remember, I need a good initial guess for the molar volume of the vapor. Remember that there's 3 possible solutions for the molar volume of the vapor and the molar volume for the liquid. And what I think could potentially be going on is Excel is finding the middle value or not finding the value that I want. So I'm going to go back in my Excel spreadsheets, and I already have a spreadsheet that will plot the molar volume as a function of pressure. Sorry, the other way around, right? Plots pressure as a function of molar volume. This is something that we did in the first half of the course. So I copied my A and B parameters for N-butane, and I'm going to use the pure component as the base case. So this is all the way back on sheet 1 from this ever-growing Excel sheet, where my problem was to find the molar volume of N-pentane at a certain temperature and pressure. So what I did is I copied these just now. So I copied my A and B parameters. These are in units of meters cubed, pascals, and moles. And this Excel spreadsheet is set up to do bar centimeters to the 6 per mole squared and centimeters cubed per mole. So just in the cell below, I converted the units from SI units to bars centimeters 6. So what I'm going to do is simply save my Excel spreadsheet, because I don't want to mess everything up, or I want to go back to this maybe in the future. But I just want to see what happens if I plot this. So instead of whatever value that is, I'm going to copy in the parameters for N-butane. And what now? Oh, I have to change the temperature to, what was it, 323.15 Kelvin. And my pressure pressure, what's pressure should be? I was going back and trying to remember in this sheet. I would think with this sheet we were comparing the ideal gas law pressure to the actual pressure. What I want to do is adjust this plot so I can get a better idea of the pressure versus molar volume. So what I'm doing here is I'm plotting P as a function of molar volume. So I'm just selecting a range of molar volumes and then calculating the pressure based on that. So it's going to give me the pressure of the liquid and the pressure of the vapor given whatever the molar volume is. So I need to zoom in on my graph here. So I'm going to format axis and zoom way in. So maybe 2000. And for pressure, I have no reason to do that high of pressure. So maybe -1 to 10. Okay, so this is going to tell me now that I know that my vapor pressure has to be 4 bar. So what is my molar volume at those points? So it's giving me, oh, I know, it's got to, my P calc was about 4 bar. I'm going to use goal seek now to figure this out. So format axis 3000. Zoom out a little bit more so I can get all 3 roots for a pressure of 4 bar. All right, so I want this solution and this solution, however far off it may be. So remember, this is what we're using goal seek for. So I'm going to goal seek to about 6,000 centimeters cubed per mole. Obviously, we're going to have to fix that and convert it back again. So data goal seek is under what if analysis. Set cell to value of 4 bar by changing cell molar volume. Cell must contain a formula. Oh, set cell 4. Wait, B15. What's going on? I got it. So this P had a formula in it. I changed it to a number, which you can't do if you want to goal seek. So now I'm going to goal seek that formula to be equal to a value of 4 by changing the value of V. So it's not exact, this is not going to give me an exact number, right? But I said it's about 4 bar. It's not exactly 4 bar. So a molar volume for the vapor should be 6,000 centimeters cubed per mole, which if I convert it, so equals 6,042 centimeters cubed per mole. I want to convert that by dividing by 100 cubed. So 0.006 should be my molar volume for the vapor. All right, so in Phi-Phi modeling, this VV should be 0.006. I wonder if that's going to help anything. So before I go on, I want to also do the molar volume of the liquid as well and make sure that it's okay. So I'm going to make an initial guess. Remember, I want this solution, not this solution. So I want to guess on this side of 500. So if I say 300 now and do the same thing where I goal seek to value of 4 by changing the value of the cell molar volume, what do I end up getting? 831. See, it still gives me this value. I don't know why this is the closest root that it found. It's got to find this root. So I'm going to try again, maybe guess a lower volume. Say, what if analysis goal seek to value 4 by changing the value of the cell V? Still giving me 831. What happens if I try something super low? Come on, goal seek. This may be what's happening. 56. That's not it either, is it? It's not 56. It should be somewhere around 300. No? Let's see, 300. Nope, that's negative 250. Just guessing by hand at this point. All right, so this isn't working out either, and I'm not particularly sure why, and my eyes are starting to get tired from looking for mistakes. I've tried to zoom out and try and see what the whole shape of this function looks like. I've got some weirdness going on here. Again, what I'm trying to do is I'm trying to find what the molar volume of the liquid phase should be such that I can plug it into my equation with some accuracy. I suppose what I could do, that's one more thing I could try is looking up the density of N-pentane. All right, I wanted the molar volume of the liquid for pentane. So what I did is I looked up the density and I looked up the molecular weight, converted it to the proper units, and the molar volume should be the molecular weight divided by the density. So let's plug this in and see if it'll help give us a little bit more of an accurate first initial guess, 0.000101. All right, and we'll try solver again. Not very hopeful, but maybe. Set objective of R10 equal to value of 0. No, R9. Whoops, I didn't finish my solving. By changing variable cells, these all have to be a 9. And I'm hoping this works out to 4 bar. Subject to the constraints, change the constraints there. All right, a number error. It's giving me a negative pressure. All right, as I said, I think I'm about ready to give up on this problem. So even though this didn't work out, I hope that there's still some takeaway lessons that you can take. And the first is that even though I feel like a failure for failing to get this problem right, I think the number one lesson that I'd like you to take away from this is that it's okay to fail every once in a while. It happens to everybody, not something to be ashamed about, even though I just said that I was. Not really, though. All right, the second takeaway that I want to bring to your attention is that when you know something is wrong, it is much better to acknowledge that it's wrong and try to discuss ways that you think you can make it better, rather than turning a blind eye to it and just submitting something that is wrong. So I've touched on that a couple of times, that it's much, much better to highlight the deficiencies in something rather than turn in something that you know is wrong. And then the third takeaway that I think is important is that you have to give a good effort into trying to fix it. But after a certain point, I think it's okay to stop struggling and to just say that I'm rambling. I'm going to cut it short. I'm going to do one more practice problem, and then we'll get into some other interesting topics like liquid equilibrium.